Hello students. Today we are going to discuss the topic that is haloalkane, its physical and chemical properties. We know haloalkane, if you see the structure, this is Rx. It is a polar compound. R carry partially positive, halogen carry partially negative charge. So first properties is we can write it is a polar nature. That means it is a polar compound having partially positive and partially negative charge due to electronegativity character of halogens. This polar nature is greater than alkane. The polarity of haloalkane is greater than alkane. Polar nature of your haloalkane and greater than alkane. It is higher boiling point, higher BP than alkane. Why? Because it's a polar compound having partially positive negative charge, but alkane is a pure covalent compound, non-polar. That's why higher boiling point than alkane. Boiling point, the order depends upon Ri greater than RVR greater than RCl greater than RF. This is the order of boiling point. Boiling point order is Ri greater than RVR greater than RCl because large size. This is due to larger size. Due to iodine. Iodine is larger size, that's why iodoalkane has higher boiling point than bromo, than chloro, than fluoro. This is regarding the boiling point, but boiling point of that is specific or corresponding haloalkane depends upon the straight chain branch chain. If you take R CH2 R, suppose Cl is greater boiling point than R CH CH3. Having 3 carbon, let it be R CH2 CH2. Here here it is a straight chain, is a branch chain. So straight chain compound has higher boiling point than branch chain because larger size, smaller size. This is the difference regarding the boiling point. And if you see the dipole moment order is RCl greater than RF greater than RBr greater than Ri. Why? Generally we know more electronegativity, more polarity, more dipole moment, but here exception. Why? And this one it is less than chloro due to small size. As fluorine is very smaller size, it is the smallest halogen. That's why the distance is less. So as the dipole moment is the product of what? Distance and charge. The product of distance and charge. Your distance is in case of RF is very small. That's why it has low dipole moment than RCl. In other cases, due to more polarity, due to more electronegativity, your dipole moment is more. This is very important exception you have to remember for your complete examination. Then if you increase the number of boiling point, if the number of halogen increases. For example, CCl4 has higher boiling point than C. For example, you can take like this. Here CCl4, here CH3Cl, then CS2Cl2, then CHCl3. If you see the order of that dipole moment, if you see the order of dipole moment, here depends upon the bond angle. Here the order, if you compare this one, if you compare the order of dipole moment, here the order is, first one highest is, you can say CS2Cl2 greater than CS3Cl, then CHCl3, then CCl4. So this is the order of what? That dipole moment. This is the order of dipole moment. Here only depends upon the bond angle and the polarity. Here the all bonded atoms are equal size, that is similar atoms. That's why the resultant dipole moment is 0. But here the depends upon the 3 chlorine atoms. As it has 3 chlorine atoms, the dipole moment, resultant dipole moment is cancelled. It will be less. But here the dipole moment is as 1 chlorine, the dipole moment value is more. So, and CS2Cl2, if you see the bond in the case, it has highest boiling point. If you see arrange like this, if you arrange in this way, like this, here suppose you place chlorine this side, H like this. So this dipole moment will be in this direction and this dipole moment will be in this direction. So resultant dipole moment will be bond, and on the basis of bond angle it is highest. So CS2Cl2, then CS3Cl, then CHCl3, then CCl4. This is the dipole moment order. Then boiling point, if take this, if you increase, if you change the halogen, the bond boiling point order will be, if you take, already we discussed here, if number of halogen increases, if CCl4, CCH3C like this, if number of halogen increases, then the boiling point increases. Dipole moment may be less, but boiling point increases. So boiling point order will be BP order. Boiling point order will be CCl4 greater than CHCl3. You can write like this, CHCl3. That CHCl3 greater than CH2Cl2 greater than CH3Cl. Here the BP order. This is regarding BP, boiling point. Because boiling point depends upon size. Here 4 chlorines are bonded. That's a large size. That's a boiling point is more compared to this. This is the boiling point. This is dipole moment. Dipole moment, in some cases, greater dipole moment, greater boiling point. But some cases depends upon also size. As this CCl for large size, the molecule has larger size. That's why compared to others. That's why higher boiling point. So this is the very exceptional cases. Boiling point, dipole moment order. Then stability, if you see, stability order, stability order is like this: RF greater than RCl greater than RBr greater than Ri. Because this is the bond dissociation energy. R is the larger size of iodine, So weaker bond. That's why the stability is low stability. Okay, this is regarding the stability. Stability, boiling point, and solubility. If you see solubility of haloalkane, solubility if you compare, almost very low soluble, very less soluble, because cannot form hydrogen bond with water, cannot form hydrogen bond with water. As it cannot form hydrogen bond with water, that's why very less soluble. The solubility is very less in water. Then another important thing that you write, physical state. If you discuss their physical state, the lower member are gases and higher member may be liquid, or higher member may be liquid or solid. Higher members may be liquid, solid, depends upon what? Depends upon physical, that van der Waals force. Larger size, greater van der Waals force, that's a liquid, solid. But lower member, due to small size, so almost in gaseous state. And almost lower members and your chloro compounds, lower members also colorless gas. So this is regarding your physical state, solubility, stability, polar nature, boiling point. And boiling point, melting point are also same. Greater boiling point, greater melting point. BP, MP remaining same. Greater boiling point, greater melting point. So this is regarding the physical properties of haloalkane. Now let us discuss the chemical properties of haloalkane. Chemical nature. You discuss the chemical property, chemical nature of a haloalkane. We know haloalkane structure is Rx. Rx means partially positive, partially negative. As R is carry partially positive charge, so it is attracted by nucleophile. You know, nucleophile are electron-rich species. So the electron-rich species, this is electron-rich species, can attack to carbon atom, and it is replacing the halogen RNu plus X minus. So this type of reaction will take place. This type of reaction is called nucleophilic substitution. It is called nucleophilic substitution reaction. It is called nucleophilic substitution reaction. So haloalkane shows nucleophilic substitution reaction because due to polar nature of carbon CX bond, carbon carry partial positive and X carry partial negative. That's why the bond is polar. That's why easily attacked by nucleophile. So it will be easily substituted. That's why haloalkane shows nucleophilic substitution reaction. What are the nucleophilic substitution reaction? Let us discuss. If you see suppose if you take one haloalkane, let it be, this is your haloalkane Rx. If it is haloalkane can react with nucleophile aqueous KOH. Here nucleophile is which one? Minus and plus. This is your nucleophile is OH minus. So producing ROH, alcohol. It is called nucleophilic substitution reaction. Here OH minus acts as a nucleophile, attacking the OH minus, forming ROH. Similarly, if take that ammonia, if you add ammonia here, ammonia carry also lone pair. Nucleophile means electron rich, either carry negative charge or lone pair like this. So here ammonia can be substituted in Rx. So produce ammonia is when ammonia substituted in Rx, it produce primary, secondary, tertiary amine RNH2 plus R2NH plus R3N plus R4 plus N and X minus. That means produce here, see, this is primary. First substitution of ammonia, this is primary. This is your secondary. This is your tertiary. This is called quaternary salt. So this when ammonia reacts with haloalkane, this is haloalkane reacts with ammonia forming primary amine. First substitution NH3 will attack, then HX will remove. So first ammonia molecule, then this product which is produced again reacts with Rx producing secondary, then secondary amine reacts with Rx produce tertiary. So till all hydrogen atom gets substituted by R, so forming primary, secondary, tertiary and quaternary salt. This type of reaction, this reaction is called what? Hofmann ammonolysis. This is called Hofmann ammonolysis. Hofmann ammonolysis. Very important name reaction. This is called Hofmann ammonolysis. Formation of primary, secondary, tertiary amine. Here pure amine cannot be prepared. Is very important. Pure amine cannot be prepared. Pure amine can't be prepared. This is one specific condition. During Hofmann ammonolysis, action of the ammonia with what? Haloalkane, the pure amine cannot be prepared because a mixture of amines are produced during the reaction. So with ammonia, then if you take RONA plus RO minus, this is a salt, sodium alkoxide. It is called sodium alkoxide. When alkoxide added with Rx, this is here nucleophile is RO minus and producing ROR, that is ether, plus your NX. This reaction is called what? Hop, that is formation of ether. This is called ether. This is ether. Formation of ether. Formation of ether from haloalkane by action with sodium alkoxide. This reaction is called Williamson synthesis. It is called Williamson synthesis. This is called Williamson synthesis. Your name reaction. One thing you remember, all name reaction you note down. You can use different color pen so that you can identify the reaction. Hofmann ammonolysis, Williamson synthesis. This is a very important chemical properties of haloalkane. So similarly, if you use KCN, if you use KCN here, K carry plus charge, CN minus C carry minus charge. So product is RCN. Nitrile. This type of compound is called nitrile. These are amines, this is alcohol, this is nitrile. Nitrile. This nitrile produce, but if you take AgCN, here as AgCN is covalent, it has no plus minus charge. That's why nitrogen will act as a nucleophile. Here carbon directly carry minus charge. That's why it attack to R as a nucleophile. Here nucleophile always attack to R plus. Here N lone pair attack to R. So product is R and C. That is isonitrile. This is called isonitrile. Isonitrile. Formation of cyanide, formation of isocyanide. Only difference in nucleophile. Here KCN is ionic character, carbon carry minus charge, that's why produce RCN. Here AgCN, carbon has no minus charge. Here nitrogen itself having lone pair acts as a nucleophile. So product is RNC. So this is important in reaction of what? Haloalkane with some compound having some nucleophile, or it acts as a nucleophile. So now what are the other examples? What are other reactions? Let us discuss. Have you written this one? Okay, you complete the reactions. Here are X with AgCN with KNO2. Here NO2 carry minus charge, K carry plus charge. But here in NO2, oxygen carry minus charge. That's why the product is RONO, nitrite. The product is nitrite. So similarly, if you take AgNO2, here R it is covalent. First one is ionic. That's why oxygen carry minus charge. Here as it is covalent, nitrogen having lone pair acts as a nucleophile. Product is RNO2. So it depends upon the atom which acts as a nucleophilic character, which has more nucleophilic character. So here oxygen has more nucleophilic character, here nitrogen has more nucleophilic character because having lone pair. If you add some sodium salt of acetylides, Na plus C triple bond Cr, if you add, or if you can take any CH3C, any that is acetylides, this is called acetylides, sodium acetylides derivative, then produce a higher alkyne R, then C triple bond Cr. Suppose this is R dash, it will be R dash. Higher alkyne can be prepared from haloalkane using acetylides. Sodium salt of acetylides, if you add to haloalkane, produce what? As it is minus charge, so it attack to R, forming nucleophilic substituted, nucleophilic substitution reaction, that is nucleophile will be substituted in R. Then if you take a salt R dash COOAG, silver salt, if you take, you will get ester. So product is R dash COOR. Ester is plus ester. This is also here it carry minus charge, it carry plus charge. That's why minus will attack to R and forming ester plus AgX. Side product depends upon the leaving group produced. So ester is produced, higher alkyne is produced, nitroalkane, nitrite compound will be formed. If use Rx in presence of sodium metal and dry ether, you will get what? R, here R will produce, and sodium oxide. Here what happens? Sodium donate electron to Rx, so R become minus charge. Then this R minus attack to R, forming alkane. This reaction is called Wurtz reaction. This reaction is called Wurtz reaction. Write down in different pen, Wurtz reaction. Here how many name reaction we completed now? Hofmann amnolysis, Williamson synthesis, then Wurtz reaction. Formation of alkane from haloalkane in presence of sodium and dry ether. This is called your Wurtz reactions. So similarly, what are the other reactions? If you reduce this one, if you any reducing agent if you use that lithium aluminum hydride, any reducing agent, strong reducing agent, it produce RH. RH means alkane. You get alkane. This is very important. That means haloalkane can reduce to alkane by lithium aluminum hydride. So these are some important what? Nucleophilic substitution reaction. In all cases, the product is what? Substituted product. Which is substituted? Your nucleophile is substituted to R. That means your nucleophile attack to R because R carry partial positive charge. This is called nucleophilic. So all reaction is called nucleophilic substitution reaction. But other than nucleophilic substitution reaction, haloalkane shows also elimination reaction. It also shows elimination reaction. Very important. If anybody will ask, what type of reaction shows by haloalkane? Haloalkane shows nucleophilic substitution reaction. Why? Because R carry partial positive charge. So nucleophile attack to R. But excluding this one, it also shows elimination reaction. Elimination means some group will be eliminated from this. How? You see, suppose you take one compound RCS2Br. This is one haloalkane. When reacts with here the reactant is here the reactant is a nucleophile, but here the reactant we can say it is a strong base. When you use strong base, if you use, then what happens? What is the role of strong base? It remove what? It will remove hydrogen from the haloalkane and forming alkene. It will produce alkene. Let us discuss this very important reaction. Let you take the one example. Suppose CH3 CH2Br. This is your haloalkane. Reacts with alcoholic KOH. Here it is not. Here this you see this is aqueous KOH. Aqueous KOH. Here OH minus acts as a nucleophile. In alcoholic KOH, here OH minus acts as a base. So what happens? What is the role of base? Mechanism we will discuss later. OH minus takes hydrogen from CH3, so it will produce CH2 double bond CH2 plus KBr plus water. Here the product is alkene. Here OH minus not substituted here. Here as the medium is alcoholic medium, so OH minus acts as a what? Proton obstructor. It is take proton from beta. Here this is called alpha, this is beta. It takes proton from beta carbon and forming loss of group H from beta carbon and bromine from alpha carbon, forming loss of atoms group, forming alkene or unsaturated compound, that is alkene. But if you take branch, suppose CH3 CHBr CH2 CH3 plus alcoholic H. What are the product? First type of alkene will form. As alcoholic KOH means always gives alkene with haloalkane, but aqueous KOH gives always alcohol. This is a remember difference. Aqueous medium, it is alcoholic medium. Alcoholic medium always gives alkene. So what happens here? Here bromine will remove from here, adjacent carbon, hydrogen remove. So product is CH3 CH double bond CH3. Product is CH3 CH double bond CH plus that CH3. It is one product plus, or here bromine will remove her hydrogen from first carbon. So what is the product? CH2 double bond CH, then single bond CH2, then CH3. So you see the difference. When hydrogen remove from this carbon, then produce this type of alkene. When remove from first carbon, produce this alkene. But it is observed that it is more stable. This is called two position. This is the major product, more stable. Because a substituted alkene is more stable than less substituted alkane. Here alkyl group is 1. Here alkyl group is 1 and 2 across carbon-carbon double bond. We know hyperconjugation. So it has 6 hyperconjugation structure. It has only how many? Only 2 hyperconjugate structure. But because this is alpha. This is alpha position. This is alpha. This is all alpha. Both are alpha. So it has how many alpha? 6 alpha. So 6 hyperconjugation is possible. Here only 2 hyperconjugation is possible. So this is more stable. So this is the major product. This is your minor product. This rule is called Sedgwick rule. This rule is called Sedgwick rule. Is Sedgwick rule. So elimination of haloalkane. Elimination of haloalkane follows Sedgwick rule. This is very important. Forming more substituted alkene, which is more stable than less substituted or lower substituted alkene. So this is called Sedgwick rule. So this is the important elimination reaction of haloalkane forming alkene. And which alkene will be more stable? We have to see more branching. If that more substituted, if the double bond across double bond more alkyl group are there, then it is more stable because it has more number of hyperconjugation structure. That's why we have to write the major product is more substituted product. It obey which rule? Sedgwick rule. So these are some important that chemical properties of haloalkane. So in the next class we'll discuss the preparation and properties of haloarene. Okay, thank you.